Hello everyone. Today we have discussed about electric current and its effects, chapter 10 in class 7. Before starting this video, please like and subscribe to my channel linked in Pharma. Let's start. Introduction to electric current and its effects. Electric current is the flow of electric charge through a conductor, such as a wire. It is a fundamental concept in electricity and plays a crucial role in our daily lives. When a potential difference, voltage, is applied across a conductor, electrons move in response, creating the flow of current. This movement of charged particles leads to various effects, including the generation of light in bulbs, the operation of electronic devices, and the functioning of motors and appliances. Understanding electric current and its effects is essential for grasping the principles of modern electrical systems and technologies. Symbols of electric components. Here are some common symbols used to represent electric components in circuit diagrams. Resistor. Description. A component that resists the flow of electric current, reducing the current flow and controlling the voltage. Capacitor. Description. An element that stores electric charge and releases it when needed, used for filtering, smoothing, and timing in circuits. Inductor. Description. A coil of wire that stores energy in a magnetic field when current flows through it, resisting changes in current. Diode. Description. A semiconductor device that allows current to flow in one direction only, blocking it in the opposite direction. Transistor. Description. A semiconductor device used for amplification and switching electronic signals. Light-emitting diode, LED. Description. A specialized diode that emits light when current flows through it. Battery. Description. Represents a source of electrical energy, providing a constant voltage to the circuit. Ground. Description. The common reference point in a circuit, often connected to the earth. Switch. Description. A device that controls the flow of current by either allowing or interrupting the circuit. Fuse. Description. A safety device that breaks the circuit if the current exceeds a certain value, protecting the components. Electric cell. Description. Represents a single electric cell, providing a source of electrical energy. Electric bulb. Description. Represents an electric light bulb, used to emit light when current passes through it. Switch in on position. Description. Represents a switch in the on position, allowing current to flow through the circuit. Switch in off position. Description. Represents a switch in the off position, interrupting the flow of current in the circuit. Battery. Description. Represents a battery or multiple cells connected together, providing a source of electrical energy with a specific voltage. Wire. Description. Represents a conductor or wire used to connect various components in an electric circuit, allowing the flow of current between them. These symbols are used universally in circuit diagrams to represent different components, making it easier for engineers and electricians to understand and design electrical circuits. Heating effect of electric current. The heating effect of electric current refers to the phenomenon where electric energy is converted into heat energy as current flows through a conductor. When an electric current passes through a material with resistance, like a wire, the electrons collide with the atoms of the material, transferring energy in the form of heat. This heating effect is a fundamental principle used in various applications, such as electric heaters, toasters, electric stoves, and incandescent light bulbs. In these devices, the electrical energy is deliberately converted into heat to serve specific purposes, such as providing warmth or producing light. The amount of heat generated is proportional to the square of the current flowing through the conductor and the resistance of the material. This relationship is described by Joule's law, which states that the heat, H, produced is equal to the product of the square of the current, I, the resistance of the material, R, and the time, T, for which the current flows. H equals I square multiplied by R and T. While the heating effect is essential in some applications, it is also a consideration in designing electrical circuits, as excessive heat can lead to inefficiencies or even damage components. Therefore, engineers must carefully select materials and manage current levels to ensure safe and optimal performance. Magnetic effect of electric current. The magnetic effect of electric current refers to the phenomenon where an electric current flowing through a conductor produces a magnetic field around the conductor. This discovery, made by Hans Christian Ørsted in 1820, established the fundamental relationship between electricity and magnetism, known as electromagnetism. When an electric current passes through a wire or any other conducting material, it creates a circular magnetic field around the wire. The direction of this magnetic field can be determined using the right-hand rule. If you wrap your right hand around the wire with your thumb pointing in the direction of the current flow, the direction in which your fingers curl represents the direction of the magnetic field lines. This magnetic effect of electric current is utilized in various practical applications, such as electromagnets. By coiling a wire around a core and passing a current through it, a strong magnetic field can be created. Electromagnets are used in various devices, including electric motors, transformers, and magnetic relays. Solenoids. A solenoid is a coil of wire that creates a strong magnetic field when an electric current passes through it. Solenoids are used in devices like doorbells, locking mechanisms, and electromagnetic valves. Induction. The magnetic effect of electric current is the basis for electromagnetic induction, where a changing magnetic field induces an electromotive force, voltage, in a nearby conductor. This principle is fundamental to generators and transformers. Magnetic compass. The Earth's magnetic field affects a magnetic compass needle, allowing it to align itself with the north-south direction. Understanding the magnetic effect of electric current is crucial for the design and operation of various electrical and electronic devices, and it has played a significant role in shaping modern technology and our understanding of the universe. Electromagnet. An electromagnet is a type of magnet that generates a magnetic field when an electric current flows through a coil of wire. Unlike permanent magnets, which have a constant magnetic field, electromagnets can be turned on and off by controlling the flow of electric current through the coil. The core component of an electromagnet is a soft magnetic material, such as iron or steel, around which the wire is wound to form a coil. When a current passes through the coil, it creates a magnetic field around the electromagnet. The strength of the magnetic field depends on the amount of current flowing through the coil and the number of turns in the wire. Electromagnets have a wide range of practical applications due to their controllable magnetic properties. Some common uses of electromagnets include electric motors. Electromagnets are a fundamental part of electric motors. When an electric current is applied to the coils, it creates a magnetic field that interacts with a permanent magnet, causing the motor to rotate. Magnetic lifters. Electromagnets can be used to lift heavy metallic objects, such as scrap metal in junkyards or in industrial applications where manual lifting is impractical. Magnetic resonance imaging, MRI, in medical imaging. Powerful electromagnets are used to create detailed images of the internal structures of the body. Magnetic relays. Electromagnetic relays use electromagnets to control the flow of current in electrical circuits. When the coil is energized, it activates a switch to open or close the circuit. Transformers. Electromagnetic induction is used in transformers to transfer electrical energy from one circuit to another, usually with a different voltage level. Maglev trains. Some high-speed trains use electromagnetic levitation to lift the train above the tracks, reducing friction and allowing for faster and smoother travel. The ability to control the magnetic properties of electromagnets makes them versatile and essential components in many technological devices and systems across various industries. Electric bell. An electric bell is a common electromechanical device used to produce a ringing sound when an electric current is applied to it. It consists of several essential components that work together to create the characteristic ringing sound. Electromagnet. The electric bell contains an electromagnet, which is a coil of wire wrapped around a soft iron core. When an electric current passes through the coil, it becomes magnetized and generates a magnetic field. Armature. The armature is a piece of iron or steel that is attracted to the electromagnet when the current flows through the coil. It is hinged or mounted in such a way that it can move back and forth. Spring. The armature is connected to a spring, which pulls it away from the electromagnet when the current is not flowing. Contact points. The armature has a small metal piece, called a hammer, at one end. When the armature is attracted to the electromagnet due to the current flow, the hammer makes contact with an adjustable metal strip called the contact point or the gong. Gong. The gong is a circular metal plate or cup that produces the ringing sound when struck by the hammer. It acts as a resonator, amplifying the sound produced by the vibration of the hammer. Working principle. When the electric bell is connected to a power source, the current flows through the coil, creating a magnetic field. This magnetizes the soft iron core, attracting the armature towards the electromagnet. As the armature moves closer, the hammer strikes the contact point or the gong, creating the ringing sound. Once the armature makes contact, the circuit is completed, allowing the current to flow continuously. However, as the armature is now pulled towards the electromagnet, it breaks the contact with the contact point or gong, and the circuit is broken again. This causes the electromagnet to lose its magnetism, and the armature moves back due to the spring's tension, completing the circuit once more. This on-off cycle repeats rapidly, producing the characteristic ringing sound of the electric bell. Electric bells are commonly used in doorbells, alarm systems, and other signaling devices, thanks to their simple yet effective design and ability to produce distinct audible alerts. Thank you so much for watching. Please like, share and subscribe.